Hello, Eric. Hello, Ryan. Hello, Mr. Eric. Hello, Mr. Ryan.
We're not a teacher, okay?
Yeah.
Don't
Okay.
you say mister.
Okay. So today we talk about using a binary search. Remember, we are very interested in this binary search to find out the case largest number in the array. Okay. So for example, like if this is 3, 4, 2, 1, 6, 9. What's the third largest number?
4. 3.
Sorry?
4. 3.
Third largest.
3. 4.
4 is before. 9, 6,
Oh.
4. Yeah. Okay. So one way of doing it. Any thoughts? How do we do it? We can.
Wait. Find the largest, then the second largest, then the third largest.
So any other thoughts? How are we doing it?
Ow!
Sorry. How are we doing it? We can sort the array, right? We can make this array. For example, if this is nums, yeah, we can do this. Define. Okay. Let's say k largest. Yeah. K is largest.
K.
And this is numbers. Yeah. And then there's a k, okay? So we can do this lam dot sort, yeah? So we make it in order. So that will become 9, 6, 4, 3, 2, 1, yeah? When you're doing this, the numbers will become this, yeah? And then you just need to return lambs. What? No, actually it will be the reverse. It will be because lam sort, it will be this will be 1, 2, 3. Will be increasing order. If you want to make it in the descending order, you have to put a key reverse equals true. Okay. So after this, it will become this, and then what we returns what? The third largest number. So that will be k minus 1, right? Because it starts with the 0. Third number will be 0, 1, 2, which is 4, right?
Yeah.
Right. Or if you want. If you don't want to do this, then it will become, these nums will become 1, 2, 3, 4, 9, 6. And then instead of lambs, k minus 1 is lambs minus k. You see, using the negative index. So it means I want to use the kth numbers from the other side. So the third number to the end, which is 4. Okay? So this is 2 lines of code. You can do this, so get the kth largest number in an array. But today we're going to use the binary search. So what's the complexity of that sorting? Remember?
N log n.
Yes. When we talk about sorting, it's log n log n, O n log n, because it uses quick sort. Yeah. Sometimes quicker sort combined with some other simple sort or merge sort. Yeah. Usually, when we talk about the sorting, it's O log n log n. N is the number of elements in the array. Okay? Yes? Okay. So now, if we want to do this task using the binary search, we can do it like, if I given a function like count how many equal or bigger than the x number, okay? So we can, this function, we can just do this, then you tell me what it does, okay? Can you tell me what it does? I have numbers here. Nums. If I bigger or equal than x, answer plus equals 1, return answer. Can you tell me what does it mean? What does this function try to do? This is the number we just talked about, 3, 4, 2, 1, 9, 6. And x, let's say if x is 2. So what does it mean? Answer equals 0. For I in numbers, if I is bigger than x2, then answer plus 1, return answer. What does it mean? What does this function mean? Ryan, any thoughts? Any hints? What does this mean? What's this function mean? What does it mean? answer equals 0, and then I iterate all the numbers and I check if the number is bigger than 2x.
I'll sort in the numbers.
No, and then I count. What's this? What does this read?
Count it. Count how many equal.
Okay, so what does this function do?
Count how many equal big
Than that number. So it's easy, yeah? I iterate these numbers and then I check if it's bigger than x, then I count it, right? Does it make sense? Eric, this is the very simplest function. Yeah, I iterate, I go through these numbers, I check if the number I is bigger than x, then if it is, I counter increment the answers, and I return this answer, yes? Yes? The counter. What's the complexity?
O log n.
Just O(n), yeah, because I iterate these numbers only once, right? Yes?
Yeah.
Yeah, that's very easy, okay? Very simple, O(n), okay? So now with this function,
Hello.
so now how can I do this binaries? I mean binary search. I can do this if these are numbers, yeah? These are numbers 3, 2, 1, 9, 6, 7. So now what's the minimum number of these or all of these?
1.
Yeah. So I have a left bound equals min nums, which will become 1, right? And right bound, can you guess what should I write?
Max.
We're done. Nums, which will be
9.
9. Okay, so now left bound, right bound. And if I do this meter, and then I can use the function I just created. Count how many numbers are bigger than or equal to meter, right? Yes?
Yeah.
Then, look, now I can say x equals count how many than that. If x, then here it will be binary search, yeah? Y left smaller equals right? And then meter equals, I get the meter, yeah? Left plus right divided by 2, okay? Yeah, meter. If there are more than k numbers, so what does it mean? If there are more than k numbers that bigger than the current meet number, so what does it mean? We need to reduce if there are more than k, for example, if k is 3, and if there are 4 numbers bigger, for this current meter number, if there are 4 numbers bigger than it, so I need to reduce the mid, right? So I need to increase the mid, right? Am I right?
Yeah.
Because if I reduce the mid, then the x will become bigger, which is not what we want. So left becomes mid plus 1, right? And else, can you guess what's this?
Right.
Right equals what?
Max.
Right.
Minus 1.
Yeah? Alright? Yes? Yes? Okay, then return what?
Right.
We're done. This is a special case because right. Sometimes it's returned left, but in this case we're returning right, which is because we need to minus 1 to get this boundary right. Okay? Yes? So what's the complexity of all together? This is O(n).
O log n. O n log n.
We're done.
That's what I'm trying to say.
This is O(n), right?
Yeah.
And the binary search is O log n. So all together, O(n) log n. Alright?
Yeah.
Okay, good job. Okay, let's do the coding. Turn on the light, please.
Off, you mean?
Oh, turn on the. Wait. Can you go? Are you okay?
Yeah. You call that okay, babe?
Sorry?
Need to connect. Now it's showing the QWERTY.
Right. Is it okay? Is it clean? Is it clear? Wait. Let me just. Oh. Wait. Okay, that's fine. I think that's fine. I don't need to turn this off. It's very, very clear. Okay, sit down, please. No touching. Okay, I'm going to. Can you please Good boy. Okay, sit down. Okay, look at the screen. Okay. Let's do this case large case. Okay, case largest. Case largest. Now let's do this. Let's do these numbers, which is just given some numbers. Okay, and then you tell me what's the answer. Okay. Are they duplicate? No. Okay. Define
3 is duplicated.
case largest. Case largest.
2 3s.
2 3s. Okay. Let me make it 1 3 13. Okay. So nums k. Remember we talk about the sorting. Yeah. 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 And then we can return nums minus k. Let's just try to see if it's alright. Yeah. Case largest. Nums, let's say 3. Okay, the third largest number is
Which is 7.
7, yes? Am I right?
Yeah, it's going to be 7.
I think I have a spelling error. So case largest. K keys largest. Okay, so that's not what I want. Seven. Alright? Yes?
Yeah.
And you can do this using sort the other way, which is, and then you tell me what should I do, okay? Reverse. Reverse. When I say reverse equals to is sorting from the biggest to the smallest. So what should I put here? What should I put here?
Okay.
Yes, we're done k minus 1 because it starts with a 0, okay? Am I right?
Yeah.
Let's try if it still prints a 7. I have a duplicate. Duplicate unnecessary bracket, closing bracket, too many closing bracket. Yeah, 7, yeah? Okay, now let's try the binary search. Okay, so let's delete this. Remember, we talk about we need to define the function. Define count. Let's just do it count, okay? Nums k. Comes x. Then you tell me answer equals 0 for I in nums. If I bigger or equal x, what should we do here? Answer plus equals 1, right?
Yeah.
And then return what? Return what?
Answer.
Well done. And then now let's do this binary search. Binary search. Case largest. Nums. Can you sit down, please? Nums k. Right? Then left equals min nums. Getting the smallest of this number, which is 1, right? Right equals max nums, which will be 13, right? Yes? Why left is smaller than right? When the boundary not meeting each other, and mid equals what?
Mid equals left add 1. Right.
And then?
Divided by 3.
Yeah, divided by 2, okay? Using double divide means that we're only interested in the integer, okay? Then x equals count nums mid. Okay, then you tell me if x is bigger or equals than k,
Yeah.
then we need to increase the mid, right? Yes?
Yes.
Then what? Left equals,
Mid 1.
yeah, and else,
Right equals mid minus 1.
okay, and return right in this case, okay? Let's see if it also prints 7, okay? Yes, well done, you see? So it's the same, yeah? It's the same. Do you get it?
Yeah.
Is it any questions so far?
No.
Are you sure?
No.
What's the complexity of the count function?
K log n log n.
No.
N.
What's the complexity of case largest?
O log n.
No, on log n, because it uses the count function. Look, the count function is on, and this binary search is usually O log n. So when you times it together, use it together, it's on log n. Am I right?
Yeah.
Yes. So what can you tell me why there are more than k numbers larger than the mid, we need to increase the mid? Because, for example, if we are interested in the third largest number, and then we found out for this current mid, there are five numbers bigger than the mid. So we are interested in the third largest number, and there are 5 numbers bigger than the mid. It means that we need to increase the mid, so this x will be reduced. Am I right? When we increase the mid, what should we do? We should search for the upper half. So that's why we set the left boundary into the mid plus 1. Then this mid will be increasing. Similarly, if they are smaller, if we are looking for the third largest number, but there are only 2 largest number in other than mid, then we need to reduce the mid. Then we set the right boundary mid minus 1. So we keep the mid will be in the lower half. Am I right? Yes?
Yeah.
Do you get it?
Yeah.
Yes. It's like a searching. It's like you make a guess from 0 to 100. And then if I say 50, if you guess some number 50, like I say if it's smaller than what I thought, you need to continue searching between 50 to 100, am I right?
Yeah.
And if I say it's bigger, then you need to search between 0 to 50, am I right? Yeah, not 50 exactly, 50 minus 1. And in the other cases, it's 50 plus 1. Do you get it? Yeah? This is binary search, very, very important, okay? Okay, good job, good job. Let's do okay, so now you can turn on the lights and do some big dancing to other people in the world, okay? Do the